Hello and welcome to week 7, lecture 3 of CO 442642 graph theory. Today we'll be discussing the Erdos Posa Theorem. So what is the Erdos Posa Theorem? Well, before we get to that, let's discuss the Heli property for trees. So here's the theorem. Let T be a tree and F a family of subtrees of T that pairwise intersect. Then that common intersection is actually known empty. So this is not too hard to prove via induction or orientation techniques. And we're calling it the Heli property because the 19th century mathematician Heli had done it in some form for convex sets in geometry. But it also works for trees. And more generally, we can actually prove the following, again, not too hard from kind of induction techniques, that let F be a collection of subtrees of a tree T, then for any integer k at least one, either there exist k vertex-disjoint trees in F, or we can find a set X of size less than k vertices in T that intersects each tree in F. So we can either find many disjoint trees in our F, or we can indeed find kind of a small hitting set or a small cover of F. And why is this a generalization? Because if you set k to be 2, then either you could find 2 vertex-disjoint trees, which won't happen if we're assuming they all pairwise intersect, or there'd be one vertex that intersects all of the trees. So clearly this is a generalization. Now, why am I bringing this up? Well, because this is kind of in the spirit of finding this duality, either finding many disjoint copies or finding a small kind of hidden set or cover. And the question we'll be talking about today is, when does a graph contain k vertex disjoint cycles? So instead of finding trees, let's find disjoint cycles. Well, is it always possible to do this? Think about it for a second. Obviously no, because if it has no cycles, if it's a forest, then our graph can't do that. Can you actually generalize this though? Can we do something that's slightly more general? So maybe again think for a moment. Yeah, you could, if it's impossible, of course, if you can delete k minus 1 vertices to get a forest, right? Because if you could delete k minus 1 vertices to get a forest, then every cycle has to contain one of those k minus 1, and it's not possible to contain k vertex disjoint cycles. So this is, in some sense, definitely an obvious kind of necessary condition is that you're not too close to a forest. And is this, in essence, the only reason, is the question we'll be talking about today, is that you're basically close to a forest? And the answer is yes. So this is a famous theorem of Erdos and Posa from 1965, which says that for every integer k at least 1, there exists an fk such that every graph G contains k vertex disjoint cycles, or an X subset of V of G with X at most fk, such that G minus X is a forest. So again, either we get many disjoint cycles, or there's a small hitting set where the fk is a constant, irrespective of G, just depending on k. Now it might not be k minus 1, as in the Heli property, but at least just some fk. And actually, Erdos and Posa figured out what the best possible fk is. It has to be at least on the order of k log k, and they showed also that it's at most also on the order of k log k, so it's theta k log k. Okay, so there's this very nice theorem of Erdos Posa, really telling us why can't we find k vertex disjoint cycles? It's because you're close to a forest. Now, how are we going to go about proving this Erdos Posa theorem, which is the subject of today? Well, we'll follow the proof in D-Stoll, which is based off the proof of Simonovich from a little while later in 1967. So just 2 years, but maybe slightly simpler. So here's how it's going to go. So first we're going to need a proposition that if G is a graph of minimum degree 3, and C is the shortest cycle of G, then C has size at most 2 log V of G. Now why is that? It's not hard to see that if you have min degree 3, and then if you don't have such short cycles, you'd have kind of expansion out, kind of a large kind of binary tree coming out of any vertex. And then if you don't have that kind of small cycle, those would all be disjoint, and then you'd have just too many vertices. So I won't prove that, but it's pretty easy. And now we're going to proceed, but I'm going to need to define some numbers. So where does this k log k kind of come from? So following distal, we'll let rk be log k plus log k plus 4, and we'll let sk be 4k rk with k at least 2, and 1 if k is 1. And why are we defining those? Well, we're going to have the following key lemma, that if H is a cubic multigraph where V of H is at least Sk, then H contains k vertex disjoint cycles. So why is this good? Well, of course it would tell you that if we were a cubic graph, kind of the cubic version of Erdos Posa, then we would just be done from this lemma. But more than that, where's the multigraph coming in? Imagine we could find a subgraph that is a subdivision of a cubic graph. Then if you're the subdivision of a cubic graph and you suppress the vertices of degree 2, you'd find a cubic multigraph. And if we knew the number of branch vertices, those degree 3 ones, was at least Sk, then this lemma would find us k vertex disjoint cycles in the multigraph and hence in the subdivision and hence in the graph G. So this will be the idea that somehow this cubic subdivision of a cubic multigraph is where we want to be. So we're going to prove this key lemma, and to do that, yeah, we needed this definition of Sk. So it's not quite important what it is, it's just, you just need that it kind of satisfies. So if you really don't want to do this precisely, you need to track that the numbers work. And so that's why I'm giving you the numbers. But if you want to read the details of the calculations, you can go look at distal. So proof of the lemma. We'll go by induction on k. If k is 1, this is trivial. So we assume k is at least 2, right? Because if k is 1, then we have at least one vertex since S1 is 1. And then since you have min degree 3, then of course you get some cycle in the multigraph. So the hard part is, showing the disjoint one. So we assume k is at least 2, and we let C be a shortest cycle of G. So you pull out a shortest cycle of G, and by our proposition, we have that C is at most 2 log V of H. Or if H is not a graph, if you're complaining, well, that only works for graphs, then C would be 2, because you'd have a diagon somewhere, a 2 cycle. And so then it's easy to check that since k is at least 2, that this inequality still holds for S, 2 or Sk more generally, because the number of vertices has to be at least Sk. So, okay, so basically our cycle is small compared to the graph, so it gives us hope that we can find many disjoint cycles. And so we'll prove this key claim, that H minus C contains a subdivision of a cubic multigraph H prime, where V of H prime is at least V of H minus 2C. So kind of we'll be able to squint and suppress vertices of degree 2 in what remains, and indeed find still a large cubic multigraph, or at least the subdivision of that. Now, I will prove the claim on the next slide, but let's finish the proof of the lemma assuming the claim. How do we do this? Well, again, here's where I'd refer you to distal, but the calculations show that V of H prime, which we know by the claim is at least V of H minus 2C, you can do the calculations and run through those numbers and show that those are at least Sk minus 1. So that's the point of setting up all those numbers. Basically, so we're subtracting 2 log VH, and it turns out then that's, the worst case would be when V of H is then actually Sk, and then if you go through those numbers, it'll show that it's at least Sk minus 1. Okay, so if you believe that, then by induction, H prime has k minus 1 vertex disjoint cycles, C1 up to Ck minus 1. And again, those pull back to cycles in G, so I won't write it like that, just let's assume they're the pullbacks. Then C plus the C1 up to Ck minus 1, their pullbacks make a family of k vertex disjoint cycles of H as desired. So then we're done. So we kind of inductively pulling out the shortest cycles and continuing to get cubic multigraphs all the way down, building our family of vertex disjoint cycles. So that's the proof of the lemma, assuming the claim. So again, I'll state the claim one more time because we'll move on to the next slide to prove it. We want to show that H minus C contains a subdivision of a cubic multigraph H prime, where V of H prime is at least V of H minus 2C. How do you do this? Well, the key is to track the number of edges. So we let M be the number of edges with one end in C and one end in H minus C. So track that number of edges. Since H is cubic, we obviously get that M is at most C. Right? If C is a cycle, has degree 2, so if you're cubic, the number of edges coming out of C can be in most C. All right, So what good is that? Well, now here's this weird proof. We're going to consider bipartitions v1, v2 of H, beginning with v1 being vc. So we're kind of saying, well, if v2 was really a subdivision of a cubic multigraph with many vertices, we'd be happy, but maybe it's not. So why would it not be? Why wouldn't we just be done? It would be happy kind of there, is it could have a vertex of degree at most 1. It could be 0, it could be 1, and then it's not really a subdivision of a cubic multigraph. So what we do in that case is we'll move such a vertex over to v1. And we'll keep doing this. So I won't write it formally, but we'll just kind of iteratively apply this. And this terminates because, well, okay, so you had this vertex with degree at most 1 in v2, so it had at least 2 edges crossing. So we're trading 2 edges crossing for at least 2 edges crossing for at most 1 edge crossing. And so we'll get a bipartition with strictly fewer crossing edges. So since the number of edges was most m, you can only do this at most m times. So we suppose that, let's say n is the number of these moves that are done, then obviously E of v1, v2 will be at most m minus n. So the number of edges, we'll lose at least 1 crossing edge each time, so the number of crossing edges when we end this process will be at most m minus n. Now, notice that H of v2 at this final stage has minimum degree at least 2. Why? Because if it had a vertex of degree at most 1, we would have moved it. And it has at most m minus n vertices of degree 2. Why? Because if they have degree 2, then they have 1 edge coming out because it's cubic, so they're one of these crossing edges. And there's at most m minus n of those crossing edges. Okay, so if you put all that together, you realize this is this subdivision of the cubic multigraph we wanted to find. Namely, we'll let H prime be obtained from HV2 by suppressing the vertices of degree 2. And this will create a cubic multigraph. And then the only question is, how many vertices does this cubic multigraph have? Well, V of H prime has to be at least V of H, except we throw away C, so we're going to minus C. Then we do these moves. There's n of those. We're going to lose n there. And then we suppressed at most m minus n vertices of degree 2. So we're going to get V of H prime is at least V of H minus C minus n minus m minus n. Now, m and plus m minus n is m. M is at most C from the top line. And so we find that this is at least V of H minus, V of H prime is at least H minus 2C as desired. Okay, so that was the proof of the claim, which then proved the lemma, and now we're ready to prove the Erdos Posa Theorem. So how does this go? Well, we're going to let Fk equal Sk plus k minus 1, right? So Sk, again, that number for these cubic multigraphs, that guarantees k vertex disjoint cycles. Now, we may assume G has a cycle, otherwise 2 would hold with X being the empty set, right? We wouldn't have to delete anything. We just have a forest. So we can assume we have a cycle. What does that mean? Well, we'll let H be a maximal subgraph of G in which every vertex has degree 2 or 3. So what is that? That's really saying it's essentially some kind of subdivision of a cubic multigraph, except it's a slight lie because it could have components that are just cycles, which if you suppressed would kind of go away. So it's really that plus some cycles. And then we'll let U be the set of degree 3 vertices of H. Okay, and then what we know is, by the lemma, we may assume that U is at most Sk, as otherwise we would find K vertex disjoint cycles in the cubic multigraph and then pull them back to G. So we're almost done, we're getting there. We now have U, so we take this maximal subgraph. U is small, it's bounded, so that's a good candidate for finding a cover of the cycles. But now we're going to have to pick up more because there could be some more cycles that don't hit U. So let's think about these cycles. Well, let C be the set of all cycles that avoid U and meet H in exactly one vertex. So think of the ones that avoid U and meet H in exactly one vertex. Now we can't just add these to get a more maximal H because they need to have a degree 4 vertex. So instead we'll just try to cover them. How do we do that? Well, let Z be the set of the vertices in H that are in such cycles. And then for every Z, in big Z, we'll pick a cycle CZ in the C, the script C, that contains Z. So we'll just kind of pick a representative, a candidate cycle for each such vertex. And then we'll let C prime, script C prime, be the set of these CZ. And the key idea is that C prime will actually have to be disjoint. It'll be a vertex-disjoint sets of cycles. If two of them actually intersected, then we'd have a path from some Z to some Z prime, and then if we added that path, we would be more maximal. Now, we're not quite done because, as I mentioned, there are those two regular components of H. And so we'll let D be the set of two regular components of H, but that avoid C, that are already done by, kind of already with the C prime. And for each of those, we'll need some cover, so we're going to pick just arbitrary XD in the V of D for D in script D. And we'll let our X prime be our Z union these XD. And then the claim there is that C prime union D is a set of vertex disjoint cycles. Obviously the D, they're different components, they're all disjoint. They don't intersect the C prime because they avoided Z. And then the C prime, as I mentioned, are disjoint because otherwise we could get a more maximal path. And now if C prime union script D is at least K, we're done because they're a set of vertex disjoint cycles, and then one would hold. So we may assume that X prime is at most C prime union D, which is at most K minus 1. So X prime is small, and now we'll let X, our real cover, be X prime union U. And it now suffices to show that G minus X is a forest, because this would be a small enough hitting set. So suppose not, let C prime be a cycle in G minus X. Then you just have to go through the cases, but it's clear that C prime has to intersect V of H, as otherwise we could just add C prime as a component, and that would be more maximal, a contradiction. Moreover, C prime has to have at least two vertices in H, as otherwise C prime would have been in the script C. So otherwise we would have had this thing where it only met H in one vertex. And then we're basically done because now we know that C prime goes between two vertices of H minus X, and so those have degree at most degree 2 in H. And so that means if you think through it, it means that there's a path between two vertices of H minus X. And that's otherwise, I should say otherwise disjoint from H. And so we get this kind of H path, and then we can just add the path H union P to be more maximal. And so that's the contradiction. So think through that. It's a little much, gets a little technical, but once you appreciate the ideas, it's very nice. And really, again, key to this type of proof was we found this cubic multigraph. We did a lemma. For that kind of case, we were finding a subdivision of cubic multigraph. And then, so we can assume that such a maximum doesn't have many branch vertices, and then it turns out we just need a couple more, this X prime, to cover the remaining kinds of cycles. So a very nice proof. Now let's move on, though, to how does this come back to minors and grids and all this graph minors theory? Well, you can generalize Erdos Posa. So we'll say a connected graph H has the Erdos Posa property if for every k at least one, there's an fk such that every graph G contains k vertex disjoint H models, or a subset X with X at most fk such that G minus X is H minor free. So remember, H models are those specific ways to find minors in a graph. So we're kind of saying we can kind of find k disjoint H minors, but you have to be precise about that, so we mean the H models. Or you can't find any such models, i.e. that you're H minor free if we remove some small set X. So why is that a nice way to think about it? Well, basically because K3 models would be essentially precisely the cycles, right? So it depends on how you define model. If you mean it in a minimum sense, then this is true. So basically, if we look at the Erdos Posa property, could we find K vertex disjoint cycles or something that gets us K3 minor free, i.e. a forest. So when you realize this, you see that the Erdos Posa theorem equivalent formulation is that K3 has the Erdos Posa property. And then the question becomes, which graphs have the Erdos Posa property? So we kind of saw that for certain maybe kinds of trees, you could apply the Heli property, but that would only work maybe when H is a tree and G is a tree. So maybe just more generally, does this also hold when H is a tree? So again, we're only dealing with connected graphs here. What about other cycles? That would be kind of saying, can I find either K, if H was C4, can I find K vertex disjoint C4 models, i.e. cycles of length at least 4, or remove a set of vertices to get rid of those long cycles? And more generally, if H was C100, it would kind of be doing that. But maybe there's even crazier graphs for which this is true. And it turns out, actually, we can precisely figure out the answer to this question, and it's a corollary of the grid theorem. This is where it ties back in. That grid theorem, which again was hard to prove, 5 or 10 pages, gets very technical, a lot of nice ideas we didn't go through. It implies this very strong generalization of the Erdos Posa theorem. Namely, the corollary by Robertson and Seymour via the grid theorem is that H has the Erdos Posa property if and only if H is planar. Right? So K3 is obviously planar, so this implies the Erdos Posa theorem, but it really answers the question much more generally. So it is true for trees, it's true for cycles, and as long as H is planar, just also true. And that's the only case. And so it maybe gives you, a semblance of an idea of why the grid theorem is hard. It's implying the Erdos Posa theorem, which we just spent a number of slides giving you some more elementary proof of, but we'll get it as an easy corollary and much more generally for all these H. So how do we do this? Well, first, we're going to do the two directions. So first, let's do when H is not planar and show it doesn't have the Erdos Posa property. For this, we don't need the grid theorem. The key is just to use the non-planarity. So let sigma be a surface of minimum genus in which H embeds. Right? So it embeds on doesn't embed in the plane, but some other surface. Let's minimize the genus of that surface. And then what you do is you take arbitrarily fat hexagonal grids G of sigma. Right, so imagine kind of a grid, let's say make it hexagonal, you could try a square, but let's do hexagonal, and fat, so meaning they're locally planar, that they have large edge width. So, we'll pick an edge width much, much larger than the f of k that the enemy is saying the Erdos Posa property holds. And what you'll notice about these large grids is they do contain an H model, right? Because we can draw H in the surface, we can do that trick now where we snap H, we take a superfine grid and we snap our H to the grid. So you can convince yourself they contain an H model, but they don't contain two disjoint H models, because if they did, then the genus is somehow wrong, right? One H model, when you delete it, it has to use up some of the cross caps and the handles. So there isn't room to put a second one in. And then what you can more convince yourself is that there's no small set x at most fk, where g minus x has no H model. So again, assuming we're taking g much, much fatter or larger than this f of k that's given by the enemy. And how can you convince yourself that? Well, so if we remove x vertices, we don't, if the grid is gigantic, we didn't really disrupt the grid. We just disrupted it, maybe like little patches here and there, but we can just kind of squint out and say, oh, we're not going to use those holes. We'll just draw our thing to avoid those little damaged bits. And this obviously would work then. So that concludes the non-planar case, that you just bet it on a surface, and that shows you don't even have it, not when k is, general, but even for k being 2. And so now we have to turn to proving it for the planar case. And here's where we're going to use the grid theorem. So how do we do this? Well, we don't actually use H, we use what I'll call HK. So let HK be the disjoint union of k copies of H. So we're going to take different copies. So, if H is the triangle, we'll have disjoint union of k triangles. And what good is that? Well, if G contains HK as a minor, then property 1 of the Posa property holds. So that we'd have actually k disjoint H models if we contain this as a minor. But, so we may assume that G is HK minor free, right? for this specific HK. But HK is planar, right? So if H is planar, then when you take many disjoint copies of H, HK is also planar. So by the grid theorem, we know it has bounded tree width when we exclude HK as a minor, which we're doing here. So the tree width of G is at most WHK for some constant WHK. And W there is to represent width. So that means that there exists a tree decomposition TV of G of width at most WHK. So we have a nice tree decomposition, again going back to this structure theorem. We're excluding this planar graph, so we have bounded tree width by the grid theorem. That's all we're doing. And now that we have that, we can use the Heli property, this general Heli property for trees, to just convince you that there's a small hitting set, or there's many different copies of H. So how do we do that? Well, for every H model F in G, we let TF be the set of vertices in the tree T from our tree decomposition, where the bag VT has non-empty intersection with V of F. So we just kind of, we're taking, all the bags that contain some vertex of F. And the point is that since H is connected, again, we're only doing this for connected graphs, that T of F is a subtree of T. Why? Because of the axioms of tree decompositions, right? So there has to be an edge where every edge has to be in some bag, so they'd have to overlap. So if you union them all, you get a subtree. And now the point is we let script F be the family of all these TF, where F is an H model. So we have a collection of subtrees F of script F of our tree T. Good. So if there exist K vertex disjoint trees in F, then you convince yourself that we're done. Then again, number one of the Erdos Posa property holds. So why is that? Because these would actually have to be disjoint H models, because otherwise, if they had a vertex in common, they'd have some bag in common from this. Okay, so what does that mean? That means that by the general Heli property lemma, there exists some x prime subset of V of t with x prime at most k that intersects all the subtrees in our script F. So we can kind of find a small set of vertices in T that cover the F. And then you just take X to be the union of the bags. So where T is an X prime, you take the union of the VT, so the bags. And then X is size at most K times WHK, that's the size of a bag. And so then you're done. And this would satisfy number two of the Erdos Posa property. Because why? You have to convince yourself then that indeed, did we hit all of the models? Yeah, that's how the definition went, right? So if we somehow haven't hit all the models, there would be a new tree that would have been disjoint from my X, and thus from the X prime, and that's not possible. All right, so that concludes our proof of the corollary. Again, what's the point is, we looked at this very nice Erdos Posa theorem, which kind of says, either can find many disjoint cycles or a small set of vertices whose removal gets you a force. And then we kind of asked this more generally, we went through a proof of that, but we asked more generally which graphs have that property when you want to find kind of H models for minors, and it turns out when H is planar, which obviously gives the Erdos Posa theorem, but generalizations to larger cycles, to trees, etc. All very nice, and it's a nice consequence of the grid theorem. Whereas if you're non-planar, you can use the surface to show you can't do that. So again, planar graphs become an answer to a different kind of question. And I think that's very nice. Again, coming from the grid theorem and the structure theory. So we'll look forward in the future to some more structure theory, but today we've concluded with the Erdos Posa theorem. So until next week, see you then.